All right, last problem for this quite long practice exam. This is a probability quantum level kind of problem, and for this particular case I chose to use an explicit quantum system, a hydrogen atom, in order to again illustrate how the probability business of the Boltzmann distribution actually works. So the hydrogen atom has energy levels, as I think probably everybody knows, where the energy of the nth level is equal to some constant, the ionization energy, divided by the quantum number n squared. And n can take on values of 1, 2, 3, and so on up to infinity, but we're only going to deal with the lowest three levels, so 1, 2, and 3 will be enough. Here this constant E sub I is the hydrogen atom ionization energy. It's 13.6 electron volts, or 2.18 times 10 to the minus 18 joules in microscopic units, or 1,312 kilojoules per mole in macroscopic units. Also, each of these energy levels, remember, has n squared states of equal energy within it. So the first part of the problem just asks us to draw an energy level diagram for this system. For n equals 1, which is at an energy of minus E sub I, right? Because if n is equal to 1 there, then that denominator is just a 1. There's only one state, right? N squared is equal to 1. And that's the 1s state, if you recall from earlier classes. For n equals 2, which has an energy E2 of equal to minus E sub I over 4, n squared, there will be 4 states, right? N squared is now equal to 4, so there are 4 states of equal energy. And for n equals 3, E3 is equal to minus E sub I over 9, and n squared is equal to 9, so there'll be 9 states. And the 4 states down here for level 2 are a 2s and 2 p's. The 9 states for level 3 are a 3s, the 3 p's, and the 3 d's, and so on. But we don't have to care about that. All we care about is how many states there are and that their energies are all equal. All right, so that's our level diagram, and we've seen that once you have a level diagram, writing out the probabilities and the partition function and everything isn't so difficult. The next part of the problem is to ask, this is actually wrong, I changed this, but I think I'll leave that alone. I think I'll just do this part B and leave part C because it's in the key anyway, and hopefully people will be able to see how that works without a lecture. So let's just do the next part. Find the probability for each of the 3 levels at 300 Kelvin. So we need to find Q. Using our level diagram, we can see that that's going to be, and now notice, this energy is minus E sub I here. So this is a situation where the zero of energy is somewhere up here. This is a situation where we have to worry about where that zero of energy is. It's not naturally at the lowest level. So I'm going to do the opposite of what I did in the last case. I'm going to choose to put the zero of energy down here at the lowest energy level. And that means that I'm going to want just the gaps between the lowest energy level and the next 2 levels up. That gap is going to amount to adding a plus E sub I to these energies, right? Because if I add a plus E sub I here, I'll get a 0. If I add a plus E sub I here, I'll get an effective energy that's equal to E sub I times 1 minus 1/4, which is going to be 3/4 of E sub I. And for the next level up, I'll get a delta E sub 3, let's call it. That's E sub I, times 1 minus 1/9, which is 8/9, times E sub I. Sorry, it's kind of crammed up in there in a corner, but I'm writing too big for the amount of space I allowed myself. So here are delta E's. Those are the quantities we're going to actually need. We're choosing delta E for state 1 to be 0. That is the 0 of energy. So our Q is going to be 1, plus the degeneracy for level 2, which is 4, times e to the minus delta U for state 2 over RT, plus 9, the degeneracy for level 3, times e to the minus delta U for level 3 over RT. And now we just have to calculate what these actual numbers are, and we can get Q. So delta U2 is equal to E sub I times 3/4, and that is equal to 1312 times 3/4. Notice in macroscopic units, kilojoules per mole, and that is equal to 984 kilojoules per mole. Notice these energies are rather huge. That's more than a bond energy. That's because we're looking at core orbitals. Even in a hydrogen atom, these core orbitals have huge energies. The energy required to go from the 1s state up to the 2s state, for example, is huge. We're going to find out that this lowest level is pretty much entirely occupied, and these upper levels are essentially empty for this particular problem. Delta U sub 3 is then equal to 8/9 times E sub I, and that's 8/9 times 1312, and that is equal to 1166.2. Let me see, did I do that right? I think I did, yes. Yeah, 1166.2 kilojoules per mole. All right. So then what's Q going to be? Well, let's calculate this delta U over RT and this delta U3 over RT, just to see if we even need to bother with these terms. If these terms are unfavorable enough, this whole end of Q will be 0, and we can just ignore it. So let's calculate these values and see what happens. Delta U2 over RT is equal to 984,000, right, kilojoules per mole, divided by 2494, right, because we're at 300K here. And what is that? It's going to be big. That's 396.6. So what that means is that this whole exponential term is e to the minus 396.6. I think we can neglect that. That's 0 for all intents and purposes. The next term is going to be even bigger, right? I mean, we could do the calculation, but why bother? Because we know it's going to be e to something minus big, and so it's also going to be 0. Q is equal to 1. What does that tell us about the probabilities? The probability for level 1 is going to be 1. The probability for level 2 is going to be 0. The probability for level 3 is going to be 0. Anytime you get huge numbers like this, then you're not going to get any population in the upper states. And just to comment a little bit further, the reason is that these energy gaps for the hydrogen atoms are many, many kTs, 400 kTs, or more, 400 RTs, if you like, in macroscopic units. And therefore, there's just not enough energy. The surroundings energy, the bath energy is tiny, is 1/400th of this gap size. And so there's just no probability of getting that much energy out of the surroundings, and therefore no population in the excited states. The last question, which I X'd out here and I'm not going to do, asks you to calculate what temperature you'd have to get to. It's obviously not good enough to be at 300K in order to get some population up here. what temperature would you have to get to in order to get some population up here, in order to get 10% population up in this next state? But I'll leave that to you and to the key rather than go through it here.